And you'll need your Chromebook the next 3 days. So be sure that you bring that charged up. Mr. Anderson will be here Thursday and Friday. Mr. Anderson. So what kind of element, whether it's a metal or a non-metal, you'll see in a minute has, or if you watch the video, it has an effect on what kind of bond is formed. So that's kind of why you're just doing an overview on that. When you get your answer, you can check it with a friend. I'll put it back on as soon as I get finished doing attendance. All right, Devin, Layla, so Jace, Wilson, Caitlin, Patty, Emily, and Mildred. All right. All right, there you go. If you need to finish it up. All righty. Y'all check it with each other. Y'all are sure you got them. Good, fine. Move on to the notes. All right. Gonna take that as we're good. Somewhere in here I have the notes. All right. So we're moving to chemical bonding. All right, so chemical bond is a mutual electrical attraction between the nuclei and the valence electron of two different atoms. So the positive nucleus of one atom and the negative valence electrons of the other ones, because they're the outermost electrons. So a chemical bond is a strong attractive force between atoms or ions in a compound. And the reason that bonds are formed are to decrease the potential energy, which in turn increases the stability. So there's some things on this set of notes that aren't in the blanks that if I were you, I would add to my notes anyway. I would, yes, sir. So there's three different types of chemical bonds that we'll kind of talk about, but we really spend most of our time on ionic compounds in chemistry. That's kind of the one that we look at the most. So I'm here recording myself. That's really necessary. Righty. So we'll be start off by ionic, covalent, and metallic will be the same that the ones that we look at. And we'll kind of just start off with an introduction for them. Ionic bonding is chemical bonding that results from the electrical attraction. So because something is positive and something is negative between the large number of cations and anions. They have a electronegativity difference of greater than 1.7. And in ionic compounds, the electrons are actually transferred. So they're either lost and it becomes a cation, or they're gained and it becomes an anion. And these occur between a metal and a nonmetal. So an example of that would be sodium chloride, NaCl. Sodium is a group 1 metal, so it becomes a +1 ion, and chloride is a halogen, a -1, so it becomes a -1 anion, and then they attract each other. So sodium chloride is stable, table salt. That's what we think of as salt, but in chemistry, all ionic compounds are salts. So that means a little bit different in chemistry. Any kind of metal, non-metal combination is considered an salt in chemistry. And we talked about electronegativity whenever we did trends. It was the ability of an atom to attract electrons to itself. And so if you look at the difference between the two atoms that are part of the bond and see how much difference that there is, that helps you categorize what type of bond it is also. So while you don't have to memorize electronegativity values, those will be given to you on a periodic table, you do have to know how to apply them. All righty. So covalent bond is the sharing of electrons instead of the transfer of electrons. So the atoms don't end up having a full charge. And this occurs between nonmetals, between two or more nonmetals. So examples of that would be CO2, carbon dioxide, C6H12O6, good old glucose made up of 3 elements, but they're still all covalently bound to each other. Under covalent bonding, you're going to have what's called polar and non-polar covalent bonding. So it's classified a little bit more. You don't have those things under ionic. So this kind of just shows you a picture of a covalently bound, a couple of covalently bound atoms. So these are the atoms that form the electrons that form the bond. One came from this atom and one came from that atom. And then they share them in the bond. So if you count how many electrons this atom had, 1, 2, 3, 4, 5, 6, 7. And then when it was able to share one more, it got 8. So it had the full valence. So that's the whole reason that they share those electrons, to get that valence and become more stable. And y'all will kind of look at some drawings of that on Gizmo on Thursday, and then we'll go more into it next week. All righty. So we have 2 types of covalent bonds: the polar covalent bond and the nonpolar covalent bond. So polar covalent bonds, and I know you've heard that word in biology with regard to water. That's when the shared electrons have an uneven distribution of charge. Electrons will spend more time with the one atom that is more electronegative. That's the definition of electronegativity, to be able to pull an electron towards yourself. So if you look at the electronegativity values and they have a difference between 0.3 and 1.7, they would be classified as polar covalent. And these types of bonds with the uneven distribution create dipoles. And dipoles are partial charges. It's not a full charge like an ion because it's gained or lost electrons. It's just the electrons have been shifted one way or another. And these are how dipoles are represented. That funny little, maybe a gamma sign. Once again, like some kind of Greek sign. And those just represent that there's a charge, but it's not a full charge. So here chlorine is much more electronegative. So it pulls the electrons toward itself and then they kind of get shared unevenly. So the chlorine has a slightly negative side and then the hydrogen would be the slightly positive side. Where do you write it? I guess wherever you can fit it in. A dipole moment has both a magnitude, so how large it is, and also a direction, and that's what this arrow represents. It's kind of like a vector in chemistry, not chemistry, in physics. They're going to have a direction, and they're also going to have a magnitude. I'm sorry. Is that an 8? This right here? Is that what you're asking me? No, it's not. I think it's called a gamma, a sign like that. It means it's a partial charge. A dipole, that's how they're represented. I believe so, but it's some kind of Greek letter. That's what I remember, but I'm going to tell you, I don't always remember correctly. Dipole represented. Let's see. Don't really see it right off the top of here. I don't know for sure what that sign is called. Gamma, I believe, but I won't promise you I won't ever ask you that. All right, a little bit simpler one is the non-polar covalent. Doesn't cause nearly as much trouble. So the electrons are shared evenly. So neither one has that charge. Whenever you have bonding between two atoms of the same element, that's always nonpolar. So that's all of your diatomics. So if you look at the electronegativity difference, which we'll do on the practice, is less than 0.3. That tells you that it's a nonpolar covalent. There tends to be a lot more polar covalent than there are nonpolar covalent. All righty. And this just kind of shows a visual of all those three different ones. We talked about electronegativity differences before, and by calculating that difference, and you can use that little scale that you have in your notes, and you can figure out what type of bond it is. But even this representation is pretty good. Here you have the complete transfer of electron, and then here you just kind of have a shift of the electron. So the electrons shift this way, so that's going to be where your electron cloud is going to be larger. Here they're shared equally, so that's why it's symmetrical. And that is your diatomic chlorine. All right, electronegativity, in case you've forgotten, it increases as you go up and across, and then fluorine has our largest electronegativity value of 4.0. You don't have to memorize these. If you look on your practice, you'll see on your very last page, you have a little periodic table that has all those different values on it, okay? So you don't have to memorize that. You have to know how to be able to apply them, and that's what we'll look at in the practice in a minute. Remember also noble gases, some of them up here don't even have electronegativity values because they would never be part of a compound, and that's what the definition of electronegativity depends upon. All right, we are now going to skip to metallic bonds. So it is on the back of your second page, I believe. We'll come back to ionic and covalent, which are a little bit more in depth. Come back to those next week. Slow at this. I know there's a faster way. Here we go. Got some metallic bonding. All right. Metallic bonding is very different from either of the other ones because in a metallic bonding, the electrons are delocalized or they're shared with all of the atoms. So that's very different from the other two types. And because of the way that they're shared, we get all those metallic properties that we've talked about before, and we'll kind of mention again today. All right, so metallic bonds occur between two metals. They can be atoms of the same metal or atoms of different metals. And the chemical bonding that results from this attraction between the metal atoms and the surrounding sea of freely moving electrons. That's kind of a word that goes with metallic bonding, sea of electrons. And they're also called delocalized electrons. And that's because they're shared with all atoms. So they don't just seem to stay around the nucleus of one atom. They're going to kind of move, they can move freely, and they'll be around the nucleus of different atoms. So metallic properties that we see because of the way that the electrons are shared are electrical and thermal conductivity. We saw from the flame test lab, because all of those were solutions where you had metal ions, that they can have a great variety of light frequencies. And that's because of the different orbitals. We've also talked about the photoelectric effect that you see with metals. That's what makes them shiny, you know, and why we want to make them into jewelry. And then they're also malleable. Remember, that means they can be hammered into sheet, and ductile or tensile strength, that they can be pulled into a wire. All of these properties are because of the way the electrons are shared. The fact that they're mobile, that they can move, and they're in very close contact with each other. Okay, sorry, I can wait. I can wait. Ready? Okay. Nope. Okay. Y'all like the time change, or y'all wanted to go back? You liked it? It's only Tuesday.
Yeah, I don't like that it gets dark quite so early though.
All right, so metals, alloys, I know that you've heard of alloys. Those are mixtures of metal atoms that are different metal atoms that are bound together. So brass is made up of copper and zinc. Sterling silver is made up of silver and copper. So what would be a reason that an alloy would be made? Like, let's say sterling silver. Why do you think a reason that would be made? It's cheaper is one thing. And also because it's stronger usually. Like gold is a very, very soft metal. If you've ever had a 24 karat gold ring, I don't know, they don't even tend to make them a whole lot. They get very worn because they're so soft. So that's like why 12 or 14 karat or 10 karat or whatever, they're an alloy. So they have something else in it to make it a little harder. And of course, then to make it a little cheaper too. So those are going to be where you're going to see the metallic bonding between different types of atoms. In mine, I wrote like alloys dash, and then I put mixture of metals held together by metal bonds. I just wrote it down underneath heat of vaporization is where I had room. And then I put those two examples. All right, we good? All right, so when you talk about the strength of a metallic bond, like which is stronger, iron metallic bond or nickel metallic bond, it's going to be dependent upon the effective nuclear charge or the nuclear charge of the metal. Sometimes that's kind of hard to measure, so you can look at values for heat of vaporization, and that's the energy that it takes to get that metal all the way from a metal to a vapor of that metal. It take a lot of energy. And in that process, then bonds are broken between the atoms. So the higher that value is, and the stronger the metal is. So that's kind of one roundabout way of being able to figure out how strong the metal bonds are. All right, if I remember correctly. So if you'll flip, I think it's the back of that page, or maybe the front of the next page. And fill in only the metallic bond part of this. Okay, you don't need to worry. We'll come back to this. You don't need to worry about doing any of these. Just fill in this last one that has to do just with the metallic bonds. We'll come back to those other ones when we cover them next week. There's a table, hopefully, somewhere. Yours is, yeah, in your notes. Well, I sort of get worried. The very last, just worry about the very last column. It just is going to summarize everything. So on the metallic bond, the electrons are delocalized and they move among all the metal atoms. So we call that an electron C. So metals are solid at room temperature except for mercury. Mercury is a metal that is liquid at room temperature. If you look at our periodic table, it's only one of the two that are blue. Has anybody ever messed with mercury? It's poisonous. It's not around that much anymore. It used to be in thermometers. But then if you broke them because they were made of glass, it would come out and it was kind of fun for kids to play with because it makes a ball. And like if you push on it, it breaks into two perfect balls and it keeps on. So mercury is a liquid metal.
Isn't it poisonous?
It is poisonous. That's what I'm saying. They don't do that anymore.
Why are they playing with it?
Because it would break. They used to put them in thermometers, and thermometers were made out of glass, and believe me, they broke a lot. And then it would get lost somewhere. So maybe a parent couldn't find it. And then maybe a kid crawling around found it later on. And then they thought it was fun. And you're right. And then it became poisonous and dangerous. So hence that's why they don't really do that anymore.
They say that the people that use the hats, the reason they got mad hats is because they used to
Because they used to what?
handle mercury.
When they made hats, you said?
That's what they call them.
I don't know that because it made them. Did not know that little tidbit of information. Then it would leak out. Kind of like when before lead paint was illegal and like they used it on babies' beds and babies tend to second chew on stuff. Then they got brain damage. Not good times. Back in the older days. Like I was gonna say something else, but if I was, I forgot what it was. That tends to be happening a lot to me today. All right, just fill in those last couple of ones. And like I said, you don't need to fill in the first two. We will come back to those whenever we cover those two. So the quiz will be, you need to go over your notes. It's not just off the practice. We will look at the practice, but I just want to make it clear that it's not just about the practice. It's going to be 12 multiple choice questions. So. All righty, we are finished with that. And let's look just at the practice, which is really easy. I know I have it somewhere. Like I have too many things going on. Sometimes it's not worth it going out of town because you gotta get everything ready. Honors, chemistry, that's us. We're doing chemical bonding. All right, finally. All right, so it's pretty easy. You're just classifying what type of bond it is, and then if it's covalent, you're deciding whether it's polar covalent or non-polar covalent. So here you're just going to look at the compound, what elements it's made up. So nitrogen is a non-metal. And oxygen also is a non-metal. So two non-metals is going to give you what type of bond? Covalent. My next one, I have sodium, which is a group 1 metal, and chlorine, which is halogen, non-metal. So that would give me what? Ionic. Exactly. Now, if it is covalent, say what type, you're either going to need to know that it's polar or non-polar. And that's when you're going to use your handy dandy little periodic table that I printed for you. So let's look at that one. I have nitrogen and oxygen. Your difference should always be positive. So whichever electronegativity value is larger, then take that one and subtract the other one. It's also possible to get a 0 difference because that would be true for all your diatomics. All right, so if I look here, I'm looking at nitrogen and oxygen. Oxygen is 3.5 and nitrogen is 3.0. So that difference is 0.5. You don't have to write that down. I'm just going to the extreme showing it. So once I know the difference, and you look at that little chart on the front of your notes, And if it's a 0.5 difference, what is it going to be? Polar covalent. So you can just put P. So that's what I mean, that you need to be able, you don't have to obviously memorize all the electronegativity values, but you need to be able to use them when I give them to you. I wanted to show you the one that's kind of a little exception. HF is hydrofluoric acid. You don't need to write the name down. That's what we'll learn next. So you pretty soon you will know how to. That's hydrofluoric acid, and it's a strong acid, so it ionizes when it goes into water. But hydrogen is a nonmetal and fluoride's a nonmetal. So by definition, that should be covalent, right? But now I want you to go and I want you to see what you get for the electronegativity difference between those two. $1.9, right? Right about 2. 1.9. So by that definition, what should it be if you look at your chart? It should be ionic, okay? This is an exception because of the type of compound it is. Don't worry about that. For right now, we're classifying that as a covalent, okay? And I'm not going to try to give you a weird exception on the quiz either. So even though the numbers show differently for right now, for what we're doing at this level, we're just going to still classify it as a covalent. I think that's the only weird little exception on there. All right, anybody have any questions? Pretty easy. All right, y'all got a little bit of time to do some of your practice or look over your notes, whatever you want to do to get yourself prepared for the quiz tomorrow.